Good evening, guys. Welcome back to my channel. Um, yeah, yesterday we talked about BFS following the introduction of DFS as well. So now that we know the um, basic type of trees and how to traverse them using DFS and BFS, we're going to move on to optimizing these algorithms by using a technique called binary search tree. So it's a bit different from the binary search that we're going to go through um, in the next chapter or the chapter after. But binary search tree is simply a type of a tree in which left subtree has a value that's lower than the root, and the right subtree has a value that is higher than the root. And we can use this property to leverage um, the efficiency to our advantage. Um, yeah, so let's look at the problem. I'll share my screen. Yeah, so from here, the question is asking you to find the sum of values of all nodes with a value within this range of low and high. So given this range, so here it will be 7 to 15. You have to find all nodes in this tree that's within that range and then add the sum. So that would be 10, 15, and 7. So that would add up to 32. Um, you would probably solve this using DFS simply by looking through all the nodes and seeing if it fits our criterion. But since there is a BST, that's like some sort of keyword, I assume. We can use the property of BST in which the left subtree is has a lower value than the root and right subtree has a higher value than the root. Um, yeah, so how I'm going to implement this in a code. So you start from the root here, which is 10, and then you first search the left side, right? So you first search the left side. Um, no, you check the root first, and then it's within the range, so we move on with it. Um, you check now the 5, but 5 is not within 7 and 15. So it means that whatever child node that 5 has on its left side, because left side of the BFS, left side of the binary search tree, left subtree of the binary search tree means that its values are lower than its root. Uh, so that means it's going to be even way more off its range. So we can disregard this. So that means we can optimize it. And this will really help, um, not for this kind of case, but if there's way more nodes, like 100,000, millions of nodes down there. Um, but it's a big advantage that we can disregard them as a whole. But anyways, that means we're going to look at the right subtree of this 5, which is higher and might have the possibility of including a value that's within this range of 7 and 15. So we search the right subtree, which is 7. And as you can see, 7 is within the range. So we include this in our answer. So now that the search of the left side of our original root node is done, we move on to search the right subtree. And now when we go down to its child node, we see 15, which is just within our range. So we include that, but um, whatever is higher than 15 would be automatically outside our list, right? So that means we don't have to move further into this binary search tree, so that we just disregard this and we don't have to continue further. And in original DFS, we would have had to um, yes, just search through all the depths of this search tree. So that's a huge optimization once again. Um, the example two is going to be solved with same logic. So how are you going to implement this in a code? Mm, so let me start. So just like implementing our normal DFS, we just initialize our answer as 0. Now, um, mm, in a DFS, because we have to use the recursive approach, we have to regard function as uh, some kind of black box, right? So will uh, it will give us the answer what we input in the function, but we don't know what kind of um, we just assume that the function will do what we are supposed to do. So that would be, in this case, answer plus the when we're going through the left side, that would be self dot range sum bst uh, root, because we're searching the left side, root dot left, and low and high. So we're just searching within this range, and yeah, and then we will also at the right side, so that will be root dot right, low, high. Uh, when we return, now if we run this, it will work, but uh, given that we are supposed to use the property of the BST, um, it would be best to add some kind of condition that would simulate that, so that when the left side is uh, lower than the root value, then we add the uh, the we move on with the search, or if the right side is higher than the root node, then we move on with the search. So in this case, that would be if low is lower than root val, then this, and if uh, oh sorry, also it wouldn't have worked because we didn't really specify the range, so that was initially low with root val, so then hence root val. So yeah, this is like, yeah, so yeah, exactly. And now we're adding the property of the binary search tree. So if low is lesser than root val, we add to the answer the recursive range sum BST of root left. If root val is lesser than high, then right. Yeah, if the value is uh, the value of the root is lesser than the maximum of the list, then it means that it has still a capability of adding um, capability of searching the right side of its node, because um, it might still be in the range of that list. So yeah. And we also have to make sure that we add the base case here. So that will be, if not root, then return 0. Now let's see if this works. Yeah, so as you can see, it gives us the value. Yeah, so I guess if I am really solid with DFS and BFS, it shouldn't be a problem. But just in case, if an interviewer in a coding test asks you to uh, proceed with more optimization, then I guess we can add this condition to only check the the left side or right side if it's still within its list, and that's also following the property of the BST. Left side is uh, less subtree is has a lower value than its root, and the right subtree always has the higher value than its root. All right, that was it for today, I guess. It was a quick um, overview of the binary search tree. I'm also excited now that we're speaking about binary search tree. I'm also excited when we will go through the binary search, which will be a bigger topic. And uh, yeah, uh, we'll do that sooner or later. Thank you guys for listening, and I'll see you guys tomorrow, maybe with some examples or new topic with a graph.